All right. Welcome everybody to the second Christ College Engineering Society lecture. So welcome everyone in person, welcome everyone on Zoom. Today we will be inviting Claudio Galeazzi. He is the head of the CIMR project at the European Space Agency. And today he'll give us a wonderful presentation upon what he does and presents new ideas to us about the European Space Agency. So without further ado, I'd like to invite Claudio to the stage. Yeah, anywhere. Yeah, but the frame's over there.
Thank you, Adi, for inviting. It's a pleasure to be here. Yes, I work at European Space Agency. I think most of you know NASA, what NASA is. Almost no one knows ESA, I guess, which is a pity. And my objective today is exactly this one, to trigger to you that some curiosity and to show what we are doing in the largest Europe. You see the flags underneath my slide. There is also UK flag. There are flags from nations which do not belong to European community, for example, Switzerland, Norway. So European Space Agency goes beyond the European Union itself, and UK is one of the most important partners. So basically, what do we do? We are an organization of 5,000 employees, 22 nations plus associated. For example, Canada is associated, although it's not part of Europe, of course. We want to explore and use the space only for peaceful purpose, which is obvious to me. We have a headquarters in Paris, 7 sites across Europe. I will show you where, including UK, plus one in French Guiana, South America, from where we launch. And our budget is about 7 billion per year, which means 12 euro per citizen. Now, believe it or not, you or your parents paying taxes, you are spending these 12 euros a year for a space. Now, the objective is to show you what we do with these 12 euros, and I hope this will convince you. So, basically, it's a collaboration among different nations. We are active end-to-end, okay, from conception of the system to developing, to launching, to operating and exploiting data. I will show you in which sectors we are leaders worldwide. And so far we have launched about 80 satellites, okay, plus 220 launches from Group. Okay. Now, why do we do this? Basically, I would say for citizens, as a first. You as a citizen, you benefit in terms of meteo, you get the meteo forecast data, a lot of navigation. I will talk about navigation, your GPS or Galileo system, which is on your mobile. The economy, of course, benefits. About 10,000 people work in space in Europe. One very important objective is to make our planet healthier and safer. And of course, to inspire generations like you of bright and talented people, and to develop technologies for the industry. So we started in 75 with 10 nations. Now we are 22 nations. I circled in blue where the sites in Europe are, and as you see, every major country in Europe hosts a location. In UK, it is in Harwell, close to Harvard. This is the budget per nation. The budget is more or less proportional to a GDP of each nation. And as I said, yes, for 12 euros, you say, okay, I might buy a pizza. Well, I think what I'm going to present today is a 4-season pizza. So with 4 different tastes. We'll go through the journey one by one, and then you can pick up with the one which you like the most. So we start with the yellow one, which is called officially enabling and support. Basically, is our core activity. It is where everything started. So developing technologies and launching something. So launchers are also fall under the name official of space transportation. We have a family of launchers, large, medium, and small. Maybe you have heard talking about Ariane. Ariane is a company which has developed Ariane 1, 2, 3, 4, 5, and now we are developing Ariane 6, so it's the 6th model. The small launcher is bigger, Okay, and the middle one is Soyuz, derived from Russia, which has been Europeanized. Important, and this is something you will hear and hear and hear again, is to make Europe independent. So we wanted to have an independent capability to have access to the space. This is why we have our own base, which is owned by French nation and European Space Agency in French Guiana, and we have our own rocket because we want to be free to launch something. As I said, the launchers are the Legacy, which is one on the left, which is small, and the big one is the Ariane 5 and then Ariane 6. They share some parts, and this is where it is located. The red arrow shows that French Guiana is close to the equator. There is a reason for this. If you want to launch a geostationary satellite, you must launch from equator because you benefit from the rotation of the Earth. Launch infrastructure, as I said, is owned by us, is owned by ESA. Apart from launchers, we've been active since the beginning, since 1975, in development of technology. Technology which is developed usually on ground, but then which is used and proved in space. And here you see some example of astronauts playing with of course, they're not playing, they're making science in the International Space Station. When you develop some technology, you want to prove whether it is suitable for space or not. Now, satellites are expensive birds. So you first try on something which is small, easy to launch, easy to develop, and short in time. So we developed a series of satellites which are called PROBA, which are technology demonstrators, which have been flown, 1, 2, PROBA B, and then PROBA 3 this year. Okay, but we are also active in the development of shoebox satellites. Shoebox means 1 liter, so 10 by 10 by 10 centimeters, less than 10 kilos. 2 years to build and then launch, so pretty cheap. And then you can try also ground technology in space, whether it survives the radiation, because the environment is very harsh, the temperature extremes, and vacuum. These are big differences compared to Earth. The biggest of the centers of ESA is in Netherlands, is where I work. It's called ESTEC, European Space Technology Center. It hosts more than 2,000 scientists, engineers, physicists, and so on and so on. Here we conceive the missions. We develop a technology in various fields. I will show which are the fields which are relevant. Okay. We have a lot of laboratories, 35, I think, yeah, where we can develop and test the hardware. Plus, we have enormous facilities. We have the largest facilities, test facilities in Europe. Well, we have the largest thermal vacuum chamber, including solar simulation, which represents the sun illumination, where you can put a satellite and then the sun rotates around it. So simulates the real in-orbit condition in ground. In vacuum, I mean. So it's really a test which lasts weeks. Every satellite must undergo this test, because if they don't pass the test, they are not suitable to be launched, of course. And then we have the loudest sound system, because when we are in the fairing, the noise is terrible. It's 140, 150 dB. Okay, so all the large surfaces are shaken, and sometimes they break. So before launching something, you need to test, and test. So then we have the most powerful hydraulic shaker in Europe, 6-axis, controlled in 6-axis, very complex, in which you can shake satellites up to level of 10 to 20 G. So very harsh acceleration environment. Once you pass the test, then you can fly. Operation. Once you launch, you separate the umbilical from launcher, then the bird is there, and then you must talk to it, understand how it feels, what's the health, receive his messages, send him your command, and commanding in order to execute the mission. So you need a lot of equipment. You need big antennas to talk, and if the satellite is around the Earth, okay, antenna it can be that size. If the satellite goes to beyond the solar planet, antennas are 32 meters, so are enormous. And then you need a proper command center, which 24 hours a day, 7 days a week, commands and control, so talks to the satellite. We have it, of course, fully independent. This is in Germany, in Amsterdam, close to Frankfurt. But in addition to a huge antennas, we are also in partnership with other institutions, including NASA, for example. So we can rely on a network of antennas which cover the whole Earth, depending on the mission, where the satellite needs to go. And here you see how we are located, and so they cover indeed the full Earth. We move to a second slice, which is the one which usually triggers imagination because it's science, exploration not on Earth, but beyond Earth, beyond solar system. So let's start with science. This is just an overview of missions, which are legacies, old, active, in development, and just a conceptual stage. You see from the sun, you move far from the sun. All these missions are aimed to investigate various aspects of the solar system. Then we have other missions which are called astronomy. So we do not observe planets, but we observe black holes, the origin of the universe, the stars, galaxies, and so on and so on. And we have plenty of satellites already launched and plenty which are being launched. And as you see, we use different wavelengths depending on what we want to observe. So we have some payloads which adopt microwave, some in infrared, some in optical, 0.4 to 0.7 microns, then ultraviolet, X-ray, gamma ray, and anti-gravitational waves. So completely different satellites. We are an agency which was funded to develop technology to push the frontier. So we are not a commercial entity. So basically every satellite is one of a kind. So the costs associated with the development are enormous. Typically, if you build 2 satellites and you spend X, 3/4 is in the prototype, which you test extensively, and then 1/4 for the recurring satellite, which is a Chinese program. Okay, so we have some records. For example, we made the first landing in a world in the outer solar system. So in 2005, we had Huygens, Cassini-Huygens zone, which then landed on Titan, which is the largest moon of Saturn. Then again, this is a record. We did the first rendezvous of a comet, which was in 14, Rosetta. We did the first landing on a comet, still on 14. Philae was released by Rosetta. Then we have taken the most accurate 3-dimensional map of a galaxy as of today with Gaia. And Planck, we took a snapshot of a relic radiation of a Big Bang. So this picture is the original one, is pretty young, it's only 380,000 years old from the origin of the universe. The science, all the science and scientific mission have as a reference center, the one in Spain. So in Spain, we receive and process the data of the scientific satellites, archive, interface with users. And then, in addition to satellites, we also have exploration. Exploration can be done in different ways, with people or with robots, and we have both. So, of course, we are a partner of ISS, International Space Station. And we can say, we are pretty proud that about 50% of the pressurized part of the station is made in Europe. So 50% of the space where the astronauts can live is made in Europe, which is very important. This one is a cupola. It's called, this was made in Turin, because we discovered astronauts got homesickness. They were very sad after months and months, and they needed to watch outside the Earth. So this was developed with glasses just to allow them, when they are sad, to look at the Earth for their mind. Astronauts come all over Europe. Here you can see the pic from UK, for example, or Luca Parmitano from Italy. Okay. We have modules which bring food and resources to a station and get back the garbage. Okay. And of course, the next frontier now is the moon. So we are part of international cooperation in the new race to the moon. And of course to Mars. So we have already sent some rovers to Mars. Some others are on the journey to go there. It's pretty long. And we also want to make a sample return of Mars to study in Europe. Now, the first slide is the one I like the most because it is where I work and on which I will spend most of the time. It's called application. And it is pretty pragmatic because you will see that a lot of things which we do here have an impact also on our daily life. First, of the application is observing Earth. This is the fleet of the satellites which have been launched so far. And there are three big families: science, Copernicus, and meteorology. And I will go one by one. Okay, we have the center. The reference center for Earth observation satellites is in Frascati, close to Rome. So let's start with science. Science not observing the sky, not observing planets, or observing our planet. We have developed different kinds of satellites to investigate different aspects of the Earth, from the gravity, or from the water cycle to ice, magnetic field, atmosphere, forest, vegetation, and so on and so on. This is Gaussian, which was an incredible satellite. It's very low orbit satellite. If you see the picture, it's also similar to an aircraft because it flies very, very low. Usually atmosphere stops at 100 kilometers. It was flying at 250 kilometers. So there is still some residual air. So there is still some residual drag. So it was an incredible challenge. And the geoid which you've seen rotating now is the most accurate geoid ever produced so far. It is precise to 1 centimeter. It's useful because this model is in your smartphone. All the smartphones use this geoid model, for example, for accurate precision. Then we launched Swarm. Swarm is interesting. There are 3 satellites which revolving around Earth and discovered a new layer, which is a liquid iron layer, 3,000 kilometers underneath our feet, and which moves and is speeding up and changes Earth magnetic field. The magnetic field is extremely important because, as you see, then interacts with all particles which are charged in our galaxy. So it's pretty important to have a knowledge. Also, it's important for navigation for a lot of applications on ground. SMOS means SM is soil moisture, but also OS is ocean salinity. So it was a beautiful mission which is creating a continuously updating map of the soil moisture, and this has a lot of application from agriculture, for example, or forestry, to ocean salinity. Ocean salinity is very important because it's one of the motor of the ocean circulation. And with ocean circulation, also the climate changes, of course, because enormous amount of water brings an enormous amount of heat. So this has indeed had a lot of pragmatic application. As you see, the picture, the shape of satellites are really different from each other, of course, which is nice and very exciting because when you start the project, it's something completely different. It is not a serious production at all. Cryosat 1 unfortunately exploded in launch, so we launched Cryosat 2, and which worked, and has produced a DEM, digital elevation model, extremely accurate of Antarctic continent. Then something which we really use in our daily life is Meteo, of course. Meteo is something which is enormous complexity and can only be predicted through an international cooperation. So all the major nations, US, China, Japan, Russia, and Europe, have decided to launch different METEO satellites in different orbit with different instruments in order to give the best coverage of the METEO, short term, mid term, any latitude in the world. So, we have two families of satellites which are already flying, and we are already building the new next generation, because the satellites have a definite finite life, 10 years, 15 years usually. So we have Meteosat, which are in GEO. GEO means geostationary orbit, and the METO family, which is LEO, low Earth orbit. To give you an idea, GEO means 36,000 kilometers on the equator. LEO is 600, 700 kilometers above Earth. So the LEO satellites make 15 revolutions a day around the Earth. So they really go fast. We have a lot of them flying. And then, okay, I work on this is the program in which I work, which is called Copernicus. It's an enormous program for Earth observation. It's the biggest one, I think, is the program in which we are above US in terms of number of satellites and capabilities. Americans are pretty ambitious now, and they have just allocated some funds to start the program, which is very similar to Copernicus, but they will take some years to catch up. The beauty of the program is that all the satellites which are flying, and I will show you how many, produce an enormous amount of data. We are talking about tera and petabyte, which are completely free, full access to anybody in the world, not only to European citizens. So every institution or citizen can make a request to become a user. They will get the data, and they can do whatever they want with the data, which is fantastic. So this is the ESA policy: full, free, open access to the data. So it's paid by us and by commission, we share. Usually we pay all the non-recurring, which means the development of the first satellite of any kind, and then we have some copies, some replicas, which are paid by the commission because they don't develop. Okay, and it is the European response and support to global needs in terms of environment, climate change, and security, of course. Again, European independence is of paramount importance for us, and we are contribution to a global system of systems, which is called GS. Now, I just have two minutes. Move to show it works.
High above our heads, Copernicus Sentinel satellites circle the Earth. They provide information vital to our society and economy. Take Finland, for example. Almost all Finnish trade travels by sea. Yet in winter, the Baltic is covered with ice, blocking the Finnish harbours. Satellite observations help icebreakers efficiently open sea lanes, so factories can keep on running, and Finnish citizens are ensured butter and petrol all year round. A second example. Subsidence can cause gas and water pipelines to break right where they enter houses. In extreme cases, they might even explode. In the Netherlands, satellite data is being used to monitor this ground movement, so vulnerable pipelines can be replaced in time. Finally, the Swedish Forest Agency uses satellite imagery to monitor the status of forests across the whole country. This information is used to help family owners comply with lawful best practices. This helps Sweden to support its flourishing timber industry while preserving the environment. Each case clearly demonstrates the enormous value generated by satellites. In the near future, more Copernicus Sentinel satellites will be launched, more information will be gathered, and more value will be created for Europe's citizens and economy.
This, which you see on the slide, is the first generation of Copernicus satellites, which are called Sentinels, because they act as a sentinel for our Earth. And I will spend a couple of slides for each of them, showing what they are producing right now, what is the usage of these satellites. You see the disks, some disks are full, some not. A full disk means the satellite is already in orbit and is already operating. So Sentinel-1, we have 2 out of 4, Sentinel-3, 2 out of 4, Sentinel-5B1, Sentinel-5 to be launched, and Sentinel-2, 2 out of 4, and so on. Every Sentinel, each Sentinel has a purpose, a specific purpose, and hosts one or more specific instruments, which go from microwave to visible, infrared, visible, or UV, ultraviolet. Okay. So we have a radar vision, color vision, big picture vision, monitoring of air, and so on. We observe the full Earth, all the land masses, with various frequencies, so with various colors, I would say, extracting completely different information, producing 20 terabytes a day of data, and 300 terabytes a day disseminated to the users which requested it. And we use also the different sentinels in a synergic way. For example, here we had earthquake. So no, this was an eruption. Yes, eruption, September, so 2 months ago. And we have used the Sentinel-1, which is a rather synthetic perturbator. So they produced an interferogram every fringe. So every change of color means 2 or 3 centimeters, you see. So detects movement of the Earth down to a centimeter or sub-centimeter level. Then we wanted to know also to give information to the rescue teams. Where are the clouds, for example, whether they can fly with the helicopter or not. So, and this through Sentinel-2, which sees the colors. And then Sentinel-5P monitored the evolution of a plume of sulfur dioxide. And together with our satellite, we also reconstructed a map of which roads were completely or partially damaged in order to give the helpers the right way to go to support the group. So all these services are really operational. As I said, 2 out of 4 have been launched. This is how it looks like. This is how it looks like internally. And then you see a lot of cables. There are some kilometers of cables because we have a lot of electronics, of course. We need to provide not only power, but also all the signals from box to box when you do viewing. This is the very first image which was taken in 2014. The satellite passed over the Black Sea and then over the ocean, Atlantic Ocean, and detected some bright spots. And then an analysis of these bright spots has shown that they were ships. And these ships, what were they doing? They were polluting the sea. They were cleaning the hold with all the waste petroleum, leaving, discharging the sea. This is a common practice, unfortunately, because who's going to control the deep sea in the ocean? The beauty of a satellite is that they have a swath of 100 or even 1,000 kilometers every day. So every day you can monitor the situation of the complete world. If you want to use the data, you can do other things. That if you don't want, okay, there are also some political wills which we have to fix. But so you can do a lot of things with this data. Again, you can follow the evolution of floods. And you have heard, okay, now we are in the week of COP26, everybody talks about climate change, disaster, and floods. Okay, yes, indeed, floods exist, unfortunately. And through a satellite, you can monitor every hour, let's say, how the flood evolved. So keep warning. Here is another example of oil spill generated by this was a leak in a tank, in a fuel tank. Okay, and the ship had the damage, produced an enormous, you see the scale, 10 kilometers, oil spill. And it was important to see how it was evolving, where it was going. And on the right side, again, you have an earthquake. There was a fault which is open, and you see that the colorimetric map shows that from blue to red, every change of color, blue to red, is 2.8 centimeters. So you can really detect the sub-centimeters movement of the Earth. Of course, we monitor Arctic, Antarctic, and we monitor the formation of the icebergs. So these icebergs are enormous. You see more than 100 square kilometers, so little islands which move. And this is very important for nations like Canada, for example, or Russia, which want to navigate very high latitude to predict in advance where the icebergs will go. And since we accumulate long time series of data, we provide a clear evidence of the melting of the ice and so on and so on. So just to avoid that people around the world deny the disaster which we are making, basically. So one of the key use of this data is to produce information which are extremely solid, cannot be denied, and then bring to decision makers this data, this information, and say, okay, that's the reality. Now you act. Otherwise, everything is debatable. This is a hurricane, yes, I think so. It's a cyclone, yes, okay. Yeah, we measure wind speeds, high wind speeds, so we can also monitor the evolution of cyclones. That's interesting. Sentinel-1 is a radar, which means sends a wave and receives an echo. Depending over time, can determine several things. The 3D map and the movements of the Earth over target. Now, the skyscrapers are natural targets. They reflect very well. Now, passing and passing, we noted that there is a subsidence in San Francisco. One skyscraper was built not very professional, I would say. So the pillars are sinking now, okay, 5 centimeters a year. So this has a lot of implications. Safety of people, insurance, of course. A lot of insurance companies take this data for free, and value the houses in San Francisco, for example, or in Chile, vary a lot depending on the information they get from the satellite. So the applications are really infinite, I would say. As long as you have fantasy, you find a nice application with this data. So you see only one skyscraper has red dots, which means it's sinking. The others have green dots, which means they are very stable. So, of course, we monitor the crops. Here is Thailandia. Red zones, they have 1 yield a year. Green zones, 2 yield a year. The reason is pretty simple. There is the terrain is close to mountains. There are too many rivers and so on and so on. But in this way, the nations can also plan ahead of time where is better to invest, for example. Sentinel-2 is completely different. It's not radar, it has a color vision like our eyes. This is how it looks like. These satellites, to give you an idea, are 2 to 3 tons at launch. And the size is 4 meters tall, or less. That's the height, and the size is 1.5 meters, 2 meters. Again, collecting time series, you can see the evolution of vegetation, for example, a specific region. Here is France. Something which you can only do by satellite is deforestation, for example, in Amazon. Amazonian forest is as large as Europe. You cannot monitor Amazon by bike, by car, by aircraft, not even, because it's enormous. This is a picture 89, is same location. Yeah, exactly. It's impressive. We have found a lot of interesting features. Yes, sometimes they cut the for the wood, sometimes for animals. Then we found in the Amazon forest some strange stripes, and then we investigated where drug trafficker with private jets, private aircraft landing in the middle of Brazil. So you can find a lot of things. Then, same application, you can discover in the cities, and this is done in a lot of nations, where when people build illegally houses. You take a picture 1 month later, you find something, house, okay? So, and then you go to the cadastre, you see that it is not regularly in the cadastre, and so on. So this is ISIS in the war, Iraq, burning the oil wells. It was important to see where they were burning the oil wells and where the plume would go, how it would evolve. This algae in between Finland and Sweden. When it's summer, it's hot, algae bloom. This is a problem. The color is beautiful, yes, but it is a problem for the health of the sea. It's a problem for the navigation also. So you have to monitor how the phenomenon evolves. This is Saudi Arabia. This is irrigation. In the desert, where you established an enormous amount of water pipes which rotate around wells. So when it is, these are false colors, so they are not true colors, of course. So, but depending on the color means where there is enough water or not enough water. So it's useful. With one single pass of a satellite, you realize how much you can image. And you can see, follow the evolution of events such as wildfires. This was in Australia. This was 11th of December. And then, okay, the wildfire went much, much worse. All the smoke was moving. And you observe in natural color, in infrared and shortwave infrared, and you detect different information. Then another application, penguins, for example. Now, satellites have discovered, follow the poo of a penguin in Antarctica. There is too much poo here. Okay, and then they gave the data to scientists, which realized that the number of emperor penguins was 20% more than expected, and they started following the colonies of animals. As I said, if you have fantasy, you can do many things. Sentinel-3, okay, the 3 is peculiar because it hosts not one instrument but several instruments, so it does at the same time a lot of things all together, pretty complex. It produces land surface temperature maps, coastal and ocean color, and color is associated with temperature, plankton, health of the sea, pollution, and so on. So, sea surface topography of the sea, okay, the temperature of the sea, and it also monitors fires. These are just some real images which have been downloaded. We show you how it has been applied in case of emergencies such as hurricanes or storms, fires, wildfires, and so on. So extreme temperatures. And again, with a multipath, this is UK clearly. So 28th of June, 25th of July. So in 1 month, this was a summer in which there was very, very little rain. So it was a severe drought. You can see how vegetation changes. So from greenish to brownish. Hurricanes, of course, in this case, monitoring not the wind, but the temperature. And this is dramatic information, which is the sea level rise. Now, I think all of us are aware that this is something which is really happening. So this sort of data are a fact that cannot be put in question. And the rise of the sea is increasing, as you see. And now we are almost about 5 millimeters a year. Sentinel-5P does not observe the Earth, not the ocean, not the cryosphere, but the atmosphere. In particular, the chemical composition of the atmosphere. This is a plume from eruption of a volcan, and you see the effect is really global. Also because volcanoes emit a lot of acids, which of course do not only pollute the atmosphere, but chemically react with it, so produce a lot of effects. Having different instruments and different bands allows you also to detect the different constituents of atmosphere, which is important. So you can take a picture on the same location with different instruments and see different things, different species. This is interesting. This is Gibraltar. Now, in January 2020, it was finally realized that the ships are really nasty emitters of sulfuric acid. And so what was decided to reduce from 3.5 to 0.5, okay, for SO2. SO2 is missing in this. Ah, no, it's inside. We hope that also NO2, so nitrogen dioxide, will be limited. This satellite monitors the NO2, which is related, and shows that this Mediterranean, between Africa and Spain, you see the yellow and red stripe. This is where all the ships go back and forth through Gibraltar. And you can see that emission of ships is comparable to emissions of Granada, for example, Seville, of the city. So the ships are unbelievably dirty. Okay. This famous, okay, satellites discovered years ago the ozone hole in Arctic and Antarctic, and then this information was taken on board by various nations of the world, which years and years ago decided to ban gases which were creating the hole of the zone, but then the hole of the zone became smaller and smaller. However, it's still under evolution, so it's important to monitor it because it protects us. This is in the COVID time. The satellite data have been used in COVID time to show how the economic activity of the humans has changed month to month. And this is the pollution. Okay, this is March to April, March to April, 19 to 20. After 1 year, after 1 year, the economic went down. There was a big rise, which was no. At least the air was cleaner. Okay, maybe there are better ways to make air cleaner. This is the result. With China, you see, and not whoever also the number of coronavirus cases. And as long as the number of coronavirus cases was increasing, lockdown was becoming stricter, and this affected the economies, of course. You can also see that nation to nation there are differences for how Japan behaves, from Korea, from Hong Kong, from India also. So you can also monitor actual implementation of the policies of the nations. Center 6 is a topography, which means measures the height of something, in our case, oceans. So it costs several instruments, I will not go on it. Topography is a pretty special science. Here we are talking about millimeters. Basically, the satellite passes over the Earth, again, sends a wave, gets the echo back, measures the time, so understands, okay, here is the height of the sea, but this has to be filtered by the contribution of the geoid, of the tides, and so on and so on. So it's pretty complex, I will not go through it, but again, this is one of the satellites which has demonstrated the exponential increase of the sea level. If you want to see how this is very simple one, it's a little toy. Okay, is the tank with propellant. I have some pictures. Once you develop a satellite, you test usually in Holland, in Netherlands, in France, Italy, Germany, wherever, UK, for example. Then you prepare for shipment. You go to a launch campaign. Usually we launch from Kourou. This one, no, it was launched from Vandenberg because there was a cooperation with NASA JPL. Okay. Then you encapsulate in the fairing. Then everything is taken to the first stage, the launcher, okay. Transported, and finally launched. So it's a very exciting experience. Now these are satellites which are flying or under production. There is a second generation, and I work on this one and project manager of this one, which monitors the Arctic. And this is a new series satellite, really exciting, I would say, which are due to be launched from 2025 onwards. Usually, to give you an idea, from the conception of a satellite to the launch, there is a 10 years time span, so it's pretty long story, moving from PowerPoint to launch. But it's fascinating. So far, we have discussed about observing Earth. We are also very active in the field, 2 other fields, very pragmatic, where the business lies. One is telecommunication, of course. We have developed and developing, also in partnership, some telecom satellites. The reference center is Harvard, so close to Oxford. We develop platform. Usually, a satellite is made. It's like a bus. A bus has the bus itself and the payload, which is you, a human being. And the satellite is a bus or platform and an instrument. Okay. So a platform supports the instrument, like the bus supports human beings to move, traveling to A to B. Okay, we have now, digital communication, of course. Chameleon satellites, which means fully reprogrammable in orbit according to the needs. EDRS is European Data Relay System, so a constellation of satellites around the Earth to enable communication among them. This is a key application, which is called navigation, which means GPS, basically, but GPS is the American system. Now, we can be proud that, again, we want full independence from the Americans. So we are developing or we are launching. I think we launched already 2016. I think there is a launch next month. Again, satellites. We're building our own constellation, which is important. The idea came, I think, during the Iraqi war, first one. There was only the GPS system, and it provided for free to everybody, every citizen in the world, a certain accuracy. The time was, I think, 100 meters. No, 10 meters. That's something like that. But since America wanted to guide their missiles, their bombs, so they encrypted all the signals for all the world apart from the US force. So all the world has 100 meters, which you cannot do anything, and they kept for themselves at 1 meter. So we said, no, we want to be independent. Thank you. And this is the result. I think this is an enormous enterprise, of course. It's fully financed by the European Commission. In parallel now, China is already developing its own constellation because they also want to be independent. It's called Beidou. It is already working. Now, we'll go to the last slide. It's very short. It is in its infantry stage, but I guess it will become more and more important. Basically, I just have 3 slides. We're active first, space debris. We are polluted. We are polluting the Earth, but maybe you know we are polluting the space. You can say space is enormous. Who cares? Not true. We already have had crashes in space, although the space is enormous. And you have to think that every particle in space flies at around 7 kilometers per second. 7 kilometers per second is pretty much. So a sphere of 1 centimeter would absolutely kill you, of course, also an astronaut. So also from ground, we monitor all this debris, and we are able to predict when it's safe for astronauts to get out of the ISS and when not. Situation was becoming more and more critical. So United Nations established some years ago some guidelines, which are guidelines you cannot enforce a commercial operator. Okay. For example, to have early entry of an object, not to pollute, but it is not always followed, I would say. So we want to preserve access to, of humanity to space, because if we reach a point in which around the world there is a cloud of debris, which makes it possible to go out, this will be for eternity, because they will never come down. So once it's done, it's done. There's nothing to do. So this is why now we are conceiving systems to clean the space. Big hoovers, for example, really. Several ideas, magnetically, for example, and so on. So we are developing mission for this as well. In particular, there are some orbits which are very precious, which are very critical, and you cannot prevent humanity to access that orbit. Another one, okay, there are threats not man-made, but okay, nature-made. So meteoroids, for example, near objects. We are monitoring where they pass, and we are developing technologies to divert also small micro near objects. And finally, space weather. Space weather doesn't mean that it rains. It means that the solar cycle of 11 years has a profound effect on the Earth and on the satellite. Okay, so we have to monitor the field emitted from the sun, sorry, and the particles which are in the space. So that's it for now, for what is ESA. Now, closer to you, careers at ESA. We said we are 5,000 people, always looking for new resources which are motivated, excited, and talented. We look for different profile of people, for PhD, in science itself, or in engineering, or in other branches of knowledge. What can we offer? We offer inspiration, learning, a very nice environment, multicultural. As I said, we are from 22 nations. So in my team, we are from 7 nations, for example, which is very nice. We are active life, social, sport, and culture, and so on. So, of course, so we are inclusive. Engineering. Which disciplines are we looking for? Mechanical, of course, which means structure, mechanism, thermal, propulsion, material, robotics, optical, then electrical, including data handling, radio frequency, power, electromagnetic compatibility, system engineering, but usually you become a system engineer after done 10 years in some specialty. Telecommunication, software, ground system, because we have ground centers, and product assurance. Not only engineers, also physicists. So people which study mathematics, of course, scientists for Earth observation, yes, or scientists of exoplanets or solar system, or astronomers, and also people coming from a completely different background, which can be law, finance, communication, PR, more and more important, human resources, information technology, facility management. We have, and I think, a pretty interesting portfolio of opportunities, which goes from internship to young graduate, 1 year at ESA, well paid, by the way, national trainee, yes, research fellows, co-funded research. And for all this, I would invite you to have a look to the site and make your mind.